if you have some slides, we can try to share them.
Can you hear us, Dr. Das?
I think he can hear us, but I'm not sure about his microphone. So,
Maybe
Dr. Das, could you please
unmute.
yes, try to say something. Okay, we can see the slides now, which is great. Thanks.
Can you speak?
Yeah, can you hear us?
Yes.
Some statics.
Yeah, there is a noise, so it's not perfect, but
so any you are hearing any, the sound is okay?
Unfortunately, the quality is very bad. I'm not sure if you can do something with your microphone, but
Yeah, sure. Just give me 1 minute.
Okay, good. We can wait.
Now, is it better?
Yes.
I think yes, it's better. All right.
Yes.
So I just started sharing my slides. Helen, do you think we can start now?
Sure.
Okay. All right.
This meeting is being recorded.
All right. So the meeting is now recorded. So hello, everyone. Welcome to the next meeting organized jointly by quantum computing groups from Washington, Warsaw, and Toronto. My name is Paweł Gora. I'm facilitator, or one of the facilitators of this meeting, together with Dr. Sebastian Zając. We are from Warsaw Quantum Computing Group, and today we have a pleasure to host a great speaker, Dr. Soumya Das, and he will tell us about properties and applications of entanglement of indistinguishable particles. So, sounds really exciting. And as you can see, this meeting is recorded. There is also live streaming, so hopefully the recording will be also available later on our YouTube channel. And before we start, we would like to also announce our future events. So the next Saturday, there will be a lecture given by Javier Mancilla Montero about supervised learning using quantum machine learning in real-world cases. Later, in 2 weeks from now, Dr. Neil Kundu will tell about quantum communications in 6G wireless networks. In November, Anna Naden will tell about quantum pseudo telepathy. And later in November, Siwan New will tell about circuit compilation and error mitigation for near-term quantum computing. In December, Johan Voss, co-founder of Gluon, will tell about quantum computing for Java developers. And in January, so already a few months from now, Anna Naden, one of our participants, will be a speaker once again and will tell us about reversibility in classical quantum computation. We would also like to thank the sponsors and partners of this meetup. So as you can see, we have several quantum computing groups and organizations supporting us. So we are very thankful for that. And with this, I think I can stop sharing my slides. And Dr. Das, if you are ready, we can start, and the Zoom is yours. So thank you for accepting our invitation, and we are looking forward to your talk.
Yeah, thank you, Paul, for your kind introduction. Yeah, now I can share my slide. Okay, is my slide visible?
Yes, we can see your slides, or at least I can see your slides and we can hear you.
Okay. Anytime, so my slide is not visible or I am not audible, please ping me.
Okay. So maybe just one question before we start. Would you like to have this meeting interactive so that the participants could unmute themselves during? Okay, yes.
Sure.
So yeah, if there are any questions, please don't hesitate to interrupt and ask. You can also post your questions on our chat, so we can later ask during the Q&A session. So please go on.
Sure. So I will try to go through some non-technical details and some more technical details, and my aim is to understand all of us, so that understand this topic and our contribution of this topic. So anytime you can just tell me, and we can explain it in more details. Okay, so my today's talk is properties and application of entanglement of indistinguishable particle. Myself, Dr. Soumya Das. So I have done my bachelor, my PhD from Indian Statistical Institute, Kolkata, and now I have joined in Tata Consultancy Services as a security expert. So, and thank you all this meetup for organizing this event and giving me chance to talk. Okay, so let's start. Okay, so this talk is based on our following paper. Both are accepted in Physical Review A. First one is hyperorbit entanglement, indistinguishability, and two-particle entanglement solving. Another one is maximum violation of monogamy of entanglement for indistinguishable particle by measures that are monogamous for undistinguishable ones. So this is the brief overview of the meeting. First, I will introduce the topics, then briefly introduce quantum teleportation and hyperhybrid entangled state. Then I will introduce the degree of freedom traceout rule for indistinguishable particle. Next, the violation of monogamy of entanglement for two indistinguishable particle, the application of entangled indistinguishable particle, and finally I will conclude and give some future direction. So, first of all, let us start that we all know that Max Planck is the father of the modern quantum mechanics and information. But interestingly, when back in 1874, he was started his PhD journey, and he asked his advisor, Philip John Pauli, that whether he could do his PhD in theoretical physics. And the answer was, it was probably not a great idea to study theoretical physics, since there was nothing much left to do. Okay. But thankfully, Max Planck did not uh, take his advice, and finally in 1990, with the invention of the black body radiation, the quantum mechanics or the quantum theory was born. Okay, so this is a great achievement, and in 1935, Einstein, Podolsky, Rosen, this paper raises the question about the completeness of quantum theory and suggested that a theory is possible that will be complete, that is both local and deterministic. In 1964, J.S. Bell proved that no local theory, realistic theory can reproduce the prediction of quantum mechanics. Okay. Now, in this year, all these EPR paradox, Bell's theorem are so important, as we all know that this year Nobel Prize was awarded to Aspect, to the quantum information group, who has experimentally proven the CHSH inequality or the Bell's theorem, and also the one of the founder fathers like Anton with Zeilinger. All right. So this year we are very much fortunate, and all this theorem, all this quantum mechanics, EPR paradox, Bell's theorem will be very much relevant. Okay. So, okay. So what are the type of correlations? So in one half we know that the classical correlation exists, and the other half there are some types of correlation, that Bell non-locality, steerability, entanglement, discord, and coherence. And this order is the like the from strongest to weakest. So Bell non-locality is the strongest one, coherence is the weakest one. All of these are, you can say, quantum correlation. Okay, and we will mostly figure the entanglement one. This is the most popular. Okay, interestingly, it lies just in between coherence discord and steerability well-known locality. Okay. Now we will go to the main topic, that is the indistinguishable particle. So what is indistinguishable particle? So all the particles in the universe can be distinguished into non-identical one and identical one. So non-identical one particles are always distinguishable. Means two particles have some property by which we can distinguish those two particles. But identical particle can be made distinguishable, can be made indistinguishable, right? How? Let us see. So in the figure A and B are two identical particles. And you know, as they are microscopic particle, always a wave function is associated with the particle. So this is the wave function of particle A, and this is the wave function of particle B. Now we can identify these two particles by A and B by their wave function, because their wave function are non-overlapping. Okay. So now these two particles, although they are identical, they can be distinguished by their spatial location. Right. But if the two particles.
Sorry, what is S1, S2, S3? What is it?
So S1, you can say this is the maximum probability that of finding this particle. You can say the 90% probability. Right. So, and S3, I am just dividing this region. Okay. So S1, you can say that this is the 90% probability of finding A. So practically what we do, we did not get the 100% probability, right? Say in this domain. So identically, this line is extended up to infinite, right? So this is the ideal case. But in practical, we have to just terminate, cut down these lines. Okay. So this is, you can say, the 90% of the occupancy is you can say can find in S1. And this is similarly S2. And you can say there S3, there are no A and B particle are exist.
Is distinguishability a binary property, or can you be sort of partly distinguishable? Are there different degrees of distinguishability? That's what the slide looks like.
Here we are, you are right that this can be partly distinguishable, but here we are considering the binary property. So either become they distinguishable or they become indistinguishable.
Yeah, but
you can.
Sorry, could you tell which property you takes? What do you mean by particle, and which property of this particle you define that you can define it as non-identical or identical? Because I don't know in physics something like it is.
Right. So here you can say that this is the so for each particle there is associated a wave function where you can find this particle. There is the maximum probability of finding this particle. This area is S1, right? And for this particle, this area is S2. When S1 or S2 are non-overlapping, then you can identify, okay, the particle is in S1, we can label it by A. The particle is in S2, you can label it by B. As these two particles are completely identical, so we cannot distinguish them by any of their properties. We are distinguishing them by their spatial property, right? So in figure B, you can say that these two wave functions are overlapped in S3. So you cannot identify these particles uniquely, right? Because they all are in S3. So then they become indistinguishable, right? So you cannot distinguish this particle in their internal property, neither their internal property nor their spatial, any of the spatial properties.
Right? A question.
Yeah, sure.
What we've discussed so far, does this apply both to bosons and to fermions, or just to?
I will discuss this, but this applies to both bosons and fermions.
Okay.
Okay. Surely I will discuss that. You will later see that where this applies to boson, where this applies to fermions, but in general, this applies to both bosons and fermions. And a recent particle is discovered, as you know, anions, and I don't know about that, whether what this anion is, and this is an interesting future work, you can say. I'm just telling, I was about to tell this at the end of the presentation, but all my discussion is related to boson and fermion, and this can be extended for anions also, if you know that what anion particle is. Okay. Okay, so this is the most interesting slide, and when I read, I was also confused here a little bit. So yeah, any more questions? Then I will move to the next slide. Yeah, thank you. So let's move to the next slide. Okay, now we will understand quantum teleportation and hyper-rapid entangled state. So most of us knows that what quantum teleportation is. So I am not discussing this. So what I am telling here, see, so here I am discussing that most of quantum information, as we know, that are for mostly distinguishable particles. Now in few years, say 2016, 2017, 18, these properties and application are now people are trying to do for indistinguishable particles. How this quantum teleportation was proposed in 1993 for distinguishable particles. These are now proposed for indistinguishable particle in 2018. So this is the paper number. EPR steering again proposed in 1935. Again, this was proposed for indistinguishable in 2018. Entanglement swapping proposed in 1993. They are again proposed in 2019 for indistinguishable. So you can see there are some properties that are previously proposed for distinguishable particle. Now they are proposing for indistinguishable particle. And again, there are some properties duality of entanglement that was proposed are again extended for distinguishable particle. So from this discussion, you can have some confusion. Okay, is there exist any quantum correlation application that is unique to only distinguishable particle or only indistinguishable particle, right? So these are the some question we can have. So we'll try to answer this question. So I think everyone knows what quantum teleportation is, but still I am just discussing it. That quantum teleportation is the transfer of quantum state and unknown quantum state from one place to another. How this can be done? Suppose A and B are entangled. If we perform some Bell state measurement jointly on A and X, and just communicate the result of this measurement to via classical communication to the location B. So we perform some unitary transformation, and then based on this classical communication and unitary transformation, we get the phi B that is previously associated with X into B. So interestingly to note that after this Bell state measurement, these two particles are destroyed. So this state is transferred to B, from X to B. So this is known as famous quantum teleportation, and the fidelity of quantum teleportation is the overlap between this initial state and the final state. So if we get exact same state, then the fidelity will be 1, and if we get some state which is close to X, then the fidelity will be less than 1, based on this formula in equation 1. Okay, here rho out is the density matrix of the output state, and rho in the density matrix of the input state, right? So in 19 with unit fidelity was proposed with distinguishable particle by Bennett. Bennett et al. And in 2018, Franco Wall shown that quantum teleportation protocol with fidelity 5 by 6. Again, Margellino et al. Has shown that it is possible to asymptotically achieve unit fidelity quantum teleportation with indistinguishable particles. So the
I have a
question is,
question.
sure.
In the original teleportation scenario,
Yes.
Bob can reconstruct the quantum state with 100% certainty, provided
Yes.
he receives the signals from Alice, the classical signals.
Yes.
So how
Sure.
can you have less than perfect fidelity?
Okay. So this is based on the joint state. So if this is a maximally entangled state, then you can have a fidelity 1. If this is not a maximally entangled state, then you have a state which is not equal to 1 fidelity. Which using, you can say, non-maximally entangled state, you cannot achieve unit fidelity. So this is the reason.
Okay, that's clear. And if there's no entanglement at all, then the fidelity is
Right.
0.
So no, there is no entanglement at all. Then the fidelity is, I think, 2 by 3. Right.
Oh, really?
So this was shown in 1994 by Jutsa paper, I think. So this is the
Okay.
bound of classical teleportation. Right. Using no entanglement, the maximum fidelity you can achieve is 2 by 3.
Okay. Dr. Das, it looks that there was also a question on YouTube, if we can ask. So there was also the answer from Anna on the chat, but maybe let's maybe ask this question. But they cannot occupy the same location when collapsed, right? They are indistinguishable as wave functions only, right? And then Anna replied, if they are bosons, they can occupy the same location, but if they are fermions, there has to be a difference between their states.
Sorry, I couldn't get the question. Yeah, let me just.
Okay, you can check the question on the chat. There was a question whether they can occupy the same location when collapsed.
Yeah, sure. So this is related to boson and fermions. So what they are telling, this is correct. And yeah, I will discuss this later. But yeah, whatever they have, anyone R9 has told, this is correct. But there is a way to make this fermions indistinguishable, right? Although in the same location, they cannot have you can say same property. Yeah, you are correct. Okay.
Question, but can you make bosons distinguishable? The alternative.
Yeah, sure. You can just make them far apart. Then they are distinguishable by their special location.
Okay, but they would have to be physically separated.
Yeah, sure. So this is what I have make this S1, S2, and S3. So in S3 there is no wave function of A and B. Okay, so then they are physically separable. Okay. And this is, you can say that this is just a schematic. In real life, this scenario is not possible. We take another trick, you can say, to make these particles distinguishable or indistinguishable. This is a theoretical model. Okay, practically we do different method to make particle distinguishable or indistinguishable. And yeah, and one thing I just wanted to share with you that this distinguishable and indistinguishable conceptually is very tricky. Okay, I will ask you that go through the reference again. If you have some question, you email me, write me. But it took me about 6 months to 1 year to understand this. What is this distinguishable and indistinguishable? So if you have still doubt, those who are having, don't worry. Just read or talk to me later. Your confusion will be clear. Okay. So, okay, yeah. Okay, so here we were saying that so here comes the open question that is it possible to perform a unit fidelity quantum teleportation using indistinguishable particle? Okay, so this is an open question, another open question. Okay, now we will discuss the hyper-hybrid entangled state. So suppose A and B are two particles. A have 2 degrees of freedom, 1 and 2. B has 2 degrees of freedom, 1 and 2. If both 1 degrees of freedom are entangled and 2 degrees of freedom are entangled, we can say they are hyper entangled state. And the different type of degrees of freedom of the two particles are entangled, say A1, B2 and A2, B1, we say hybrid entangled state. If all of entanglement are present, we say this a hyper-hybrid entangled state. So I'm defining this. Now, hyper-hybrid entangled state was first proposed by Lee et al. Using two indistinguishable bosons. So there is some open question that is HHS possible for two indistinguishable fermion? Yeah. Sorry, any question? Okay. So is HHS possible for two indistinguishable fermion? Is the scheme of Lee et al. Proposed by Lee et al. Applicable for two distinguishable particles? If not, can distinguishable particle exhibit HHS through some other scheme? So these are some open questions that came into our mind based on this paper. Okay. So this is the circuit of Lee et al. By which they have prepared this hyper-hybrid entangled state. Okay, so I'm not explaining this circuit. Let us go to the main theorem first. Okay, if quantum particle, either distinguishable or indistinguishable, can simultaneously produce and perform hyper-hybrid entangled state and unit fidelity quantum teleportation respectively, then using that, cloning of any arbitrary quantum state is possible. So this says that if any particle can have the property of both hyper-hybrid entangled state and unit fidelity quantum teleportation, then using that particle you can perform cloning. That is, the famous no cloning theorem is violated. Okay. So what are the implications of this theorem? Let us first prove this theorem. So this is a schematic of the proof. Detail of the proof and the mathematical representation you can get in our paper. So I'm just telling the schematic. Say PQ are in hyper-hybrid entangled state, and X is the unknown, arbitrary unknown state, right? If you perform a joint state well state measurement using the 1 degrees of freedom of P, and if the result is say K, and this K is transformed to the Q particle, and based on this result K, you perform two unitary UK on Q1 and Q2, then you can get this X5 state on both Q1 and Q2. So from a single state, you are getting two states. So this is the violation of the no cloning theorem. So this can happen with this HHS. You can say that P and Q are in HHS and this unit fidelity quantum teleportation. Right. So this is the proof of the theorem. The mathematics you can get. So this is a schematic proof. Right. So we have proved that HHS and UFQT, unit fidelity quantum teleportation, implies cloning. So the logical equivalence is if no cloning theorem, so in quantum mechanics, no cloning theorem is a theorem that is we assume that it is true. There is a proof that it is true. So if this is true, then either HHS is not possible or unit fidelity quantum teleportation is not possible. So if we take equation 4, we know that for the distinguishable particle, unit fidelity quantum teleportation is possible. That means for distinguishable particle, HHS will be an impossibility. Similarly, for indistinguishable particle, Lee et al. Has shown that HHS is possible. So, using indistinguishable particle, unit fidelity quantum teleportation must be impossible. So, this is the two corollaries of our main theorem, right? So, here we have found some of the answers from the previous slide, that we get a unique property such as unit fidelity quantum teleportation. This is unique to distinguishable particle, and HHS, this is unique to indistinguishable particle. Also, unit fidelity quantum teleportation is not possible using indistinguishable particle, right? So this answers question number 1, 2, and 3. So this is the broad picture. Yeah.
Yeah, no, this may have to do with the definition of indistinguishability, but two fermions cannot be in the same state, so how can they be indistinguishable? Mustn't fermions be distinguishable?
Okay, so let us assume, I am not going in that for this time. I will discuss the fermion case later, but let's assume that this discussion is for boson. Okay, so for boson this is true. I will discuss the fermion case later, but let us assume that this is for boson. So if this is for boson, then this will be true for bosons also.
Yes.
Right.
Okay. Thank you.
Sure. So I will discuss or extend this discussion for fermions later, but let us assume that this discussion is for boson. Now, if we establish that for using two fermions, this indistinguishable is possible, then all this discussion will be automatically valid for fermions also, right? Okay. So that we will do later.
Sorry, can I have one remark for maybe question? Maybe you shouldn't use name particles, but just quantum states, because we know that particles could be described by states, but not all states are represented by particles. Yes, so you have some properties that you can simply say that your quantum system is that or that, but why you call it particles? This is misleading for me in this case.
Yeah, you are true, but for simplicity, we are telling that for particles, because for if we say some quantum state, then some of may ask that, okay, what is quantum state? What is the difference between quantum state and particle? So to avoid that ambiguity, I am just telling this as particle, but whatever you are telling is true. That is more, you can say, a significant result or more minute version of seeing this. Right. And I'm telling particle on the behalf, like the quantum state is associated to some quantum particle, and we are just describing that state as a particle. But if we represent everything as a quantum state, then that will be true. That will be more true.
Yeah, but look, that you can have one state for one particle and one state for many particles. Yes, it depends what kinds of quantum system you try to describe. Yes.
Sure. So here, for simplicity, we are assuming that a quantum state is associated with one particle only, right? So that's why we are getting a one-to-one mapping with quantum state and quantum particle. But whatever you are telling that for one quantum state there can be many particles, that is very true, right? So this, or you can say that this discussion is valid for the quantum state that is associated with a single particle. Okay. Okay. Yeah. Thank you. Okay. So previously the picture was there that there was some properties and application that can be done with both distinguishable particle and indistinguishable particle. Now we have the broad picture that there are extra properties that are unique to only distinguishable particle and only indistinguishable particle, right? Say UFQT, unique fidelity quantum teleportation, only quantum distinguishable particle, and hyper-Rabbit entangled state for quantum indistinguishable particle. So the summary of this slide that no HHS for distinguishable particle, no UFQT for indistinguishable particle, and we have also proved that HHS for permission. This is on our paper. I am not discussing this. And okay, so I am moving to the another topic, that is the degree of freedom traceout rule for indistinguishable particle. Okay. So till now, we all know that degrees a traceout rule for a distinguishable particle, each having a single DOF freedom. This is all known. This is our known traceout rule, and this can be extended trivially for distinguishable particle having multiple DOF. So in 2016, Low Franco et al. Have proposed traceout rule for indistinguishable particle, but each particle having a single degrees of freedom. So our motivation is to propose the DOF traceout rule for indistinguishable particle having multiple degrees of freedom. Okay. So this is a bit mathematical. I am just not describing all this mathematics. Yeah, yeah. Sure.
The traceout rule, does that have something to do with measurement?
So traceout rule is a you can say a theoretical operator, and obviously it has to, if you want to get some experimental idea, then it has to do with measurement also. But first we know that traceout rule is a operational idea, a theoretical idea, but obviously when we implement it, this has to do obviously with measurement. So this representation of the state of indistinguishable particle. So this is the representation of the Low Franco et al. Documentation of 2016. They have given a representation of two indistinguishable particles having 2 degrees of freedom. Okay, so here the alpha A1 and A2 are 2 degrees of freedom, and these are their eigenvalue. Alpha 1 and alpha 2 are the special degrees of freedom, and these are a single particle, this is another particle, and they have represent is some wedge form notation. Okay, and this is the, you can say, coefficient of each particle. This is eta. Eta is the representation of the particles are in both either bosons or fermions. So I am not discussing this representation. For this representation, please go to the Low Franco et al. 2016 paper. Okay, so this is the representation of two particles having 2 DOF, and this is the density matrix notation, and this is the we have extended it for 2 particles having n DOF, and p particle each having the 2 DOF version. And this is the DOF traceout rule. This is a bit mathematical. I'm just telling that these are the mathematics that we have developed. The details of this mathematics is in the paper, but you can just assume that there is a DOF traceout rule for indistinguishable particle that we will use for our next result. So this is a violation of monogamy of entanglement for two indistinguishable particles. So we all know that monogamy is a rule of marriage with only one partner. Okay. So in our life, we can marry only a single partner, and this rule is known to be the monogamy rule. But interestingly, this is the first time when I was very excited that this social rule is also applied to in quantum world. This is very interesting. So I was very surprised when I read this property. So what this rule says that if two particles are maximally entangled, then none of them can share entanglement with any of the particles. So mathematically, we can write that the entanglement between A and B and the entanglement between A and C are always restricted by the entanglement between A and the joint system B and C. I hope you all know about this thing. And this has application in quantum key distribution, classification of quantum state, condensed matter physics, black hole physics, etc. So, does monogamy always hold? No. Monogamy of entanglement depends on two properties: dimension of the particle and the entanglement measure. Okay. So, for example, so we all know that for a qubit and for concurrence entanglement measure, monogamy always hold. And there are some other entanglement measure that is hold for up to some dimension. But say concurrence entanglement measure, this concurrence entanglement measure does not hold for Q-treat. So this is an example. You can say psi is at this state, and if you just calculate the concurrence of A and B and A and C, you can say this violates. So this is the, I think, 2007 paper. Okay, this is 2007 paper. Yeah. Okay. So here we will define two things, that is the maximum violation and non-maximum violation. So previously in this example, we have shown this non-maximum violation where E of AB is less than Emax. Emax is the maximum, you can say the value of concurrence or the maximum value of the entanglement measure. So if E of AB and AC are less than Emax, but their joint is more than this Emax, we can say that this is a non-maximum violation. If both of them are equal to Emax, then we say this is the maximum violation, because you cannot have the more value of this. Okay, so the most, so the maximum value of the left hand side is 2 Emax, that we can achieve if both of them are Emax. Okay. So we all know that in a quantum field with quantum mechanics or information, there is a no cloning theorem. So no cloning theorem forbids the creation of independent identical copy. This is the famous theorem of 1982. This is depends on the linearity of quantum theory, and this applies to quantum interaction, cryptography, black hole physics, etc. So here we know that this is, I think everybody knows that the maximum violation of monogamy for distinguishable particle implies the cloning of the distinguishable particle. This circuit is well known to you. I have discussed this previously. Say A, B, and AC are maximally entangled. Then if phi is the unknown state, if we have a Bell state measurement jointly on phi x and A, and this output Y is communicated to B and C, if B and C applies some suitable unitarity, if U, then these copies will be, this phi x will be copied to phi B and phi C.
A question, can you give us an example of how physically monogamy of entanglement can come about?
For distinguishable particles.
For but how would you produce, how would you violate monogamy of entanglement physically?
because this is the thing that you cannot have a maximum entanglement with A and B and A and C for distinguishable party. Right.
Did you violate
So,
monogamy by
if
connecting
you,
two C0 gates, two controlled NOT gates on three qubits? I think so.
But
I
other
think
than a mathematical computational manipulation, can monogamy of entanglement be violated in the physical domain? What would be an example?
A quantum computer is a physical object and it can have two controlled NOT gates.
Yeah, but it's still a mathematical simulation.
No, well, we'll continue this offline.
yeah,
Okay.
sure. So I just want to interrupt two guys that I am relating to the maximum violation of monogamy, not just a violation of monogamy. Okay, I have defined what is the non-maximum violation and this is maximum violation. So if you have a maximum violation, then only you can violate the no-cloning theorem. And this is vice versa also. If you can violate the no-cloning theorem, you can also have the maximum violation of monogamy. So this is only for using distinguishable particle, right? So we have proved this for indistinguishable particle also. So we will see that. Okay. So this is an apparent violation. So so here we are trailing that particle with single DOF. What is particle with multiple DOF? Say A has two DOF, 1, 2, B has two DOF, 1, 2, C has two DOF, 1, 2. Say A1 and B1 are maximally entangled. A2 and C2 are maximally entangled. Then does this violate the monogamy of entanglement? Apparently yes. If you say the broader picture, if you say okay, A and B are maximally entangled, then A and C are maximally entangled. If you ignore this DOF view, but if you go to the DOF view, you can say no. A is entangled with B1, A2 is entangled with C2. So there A1 and A2 are two different particles, so there is no maximum violation. Okay, so this is a example of the false maximum violation. And this is a real monogamy of entanglement in the DOF view or degree of freedom view. So where we can say that suppose the ith degrees of freedom of A is maximally entangled with jth degrees of freedom of B, then this ith degrees of freedom of A cannot have any entanglement with kth degrees of freedom. Okay, and this is just DOF version of the famous monogamy equation. Okay. So here what we have shown that in qubit system, okay, we are restricting our discussion in qubit system because in qubit system monogamy of entanglement is valid and valid for concurrence. So in qubit system, indistinguishability is a necessary criterion for maximum violation of monogamy of entanglement, the same measure that are monogamous for the distinguishable one. Okay, so what we have exactly shown, we have exactly given a state. Okay, so this is a physical state. Okay, so this is not a mathematical one. This is a physical state that you can create in a lab and do this experiment. I'm first of all telling this. So consider this state. So this is a physical 2-qubit indistinguishable state. This is a pretty good state. And using this state, we have mathematically, we have shown a circuit to generate this state physically using linear optical device. And mathematically, we have shown that this state violates the monogamy of entanglement for indistinguishable particles. So what we have exactly shown, say for two particles, each having two DOF. So each having two DOFs here, for two particles each having two DOF, if they are indistinguishable, then both AI and BJ are maximally entangled, and AI and you can say another DOF of B, say BJ2, both are maximally entangled. Okay, this thing we have shown in our paper. I am just telling you the result for the details of the circuit and the mathematical explanation. Please refer to our paper, and I think I have to wrap up within 40 to 50 minutes. Okay, so this is the proof sketch of our main theorem. So what from this theorem we can have that monogamy of entanglement for indistinguishable particle can be violated, and it can be violated maximally. So whereas for distinguishable case it is not possible to violate the maximum. So which is the more fundamental one, no cloning theorem or the monogamy of entanglement? So from this discussion, we can say that no cloning theorem is the more fundamental one, that this is hold for distinguishable or indistinguishable domain. But monogamy of entanglement only hold for indistinguishable domain and not for the for distinguishable domain, not for the indistinguishable domain. And another open question is, what is the application of this maximum violation of monogamy? So this we are all still searching, that what is this application, and is this violation possible for other quantum correlation that I have shown in the first slide, like steering, coherence, discord, etc. Whether this is possible. Okay. Now we will show one application of this entangled indistinguishable particle, and this is the last few applications. So this is the slide of the entanglement swapping. We all know that AB and CD are entanglement. Then using some Bell state measurement and classical communication, A and D can be made entangled. This is the famous entanglement swapping. And these are some open questions, that entanglement swapping requires 4 particles, that is proposed in 1993. Recently, using 3 particles, these 3 distinguishable particle was proposed in 2010 and 2019. And Castellin et al. Has also proposed an ES protocol with 4 particles, 4 indistinguishable particles, with BSM and without BSM for fermions. Okay. So the open question is this possible to reduce the resource, the number of particles further, say from 4 to 3 to 2? If the reduction is possible, what it will require, distinguishable particle or indistinguishable particle? Right. So this is a question.
Yes, I believe that in a previous event, someone said that you can't really have a Bell analyzer that distinguishes all 4 possibilities. Is that true?
4 possibilities means?
Yeah, the 4 components of the superposition that makes up a 2-particle Bell state. 1, 0, 1, 1, 0, 0, and 0, 1.
Yeah, that is the, you can say experimentally, this is challenging or experimentally not possible. But this is the just an entanglement swapping protocol. You can theoretically, this is obviously possible. Okay.
And again, not to beat a dead horse, but can more than two entangled particles be maximally entangled, or would they be partially entangled?
For more than 2 particles cannot be maximally entangled for both distinguishable and indistinguishable particle. That's for my understanding, as they will violate the monogamy of entanglement. What we have shown in here, we have shown for 2 particles, each having 2 degrees of freedom. So 1 degree of freedom of particle B, 1 degree of freedom of particle A is maximally entanglement with 1 degree of freedom of particle B, and and 1 degrees of freedom, 2 degrees of freedom of particle B. So here we are having two particles each having 2 degrees of freedom. So where we have shown this the maximum violation. If you have 3 particles, they cannot be simultaneously maximally entangled because of the monogamy of entanglement. If they are maximally entangled, as you can see there, they will violate the no cloning theorem. Okay. So this is the circuit for entanglement swapping using two indistinguishable particles and whole state measurement. We have proposed entanglement swapping circuit using two indistinguishable particles where we have swapped say a particle having two DOF and say 1 and 2, and their 1 and 2 DOF are entangled. We have swapped this 1 and 2 DOF, the entanglement between 1 and 2, to the other particle, the entanglement between say A and B. So this circuit is the famous particle exchange method where you can produce the indistinguishable particle, right? So this particle exchange method was proposed in Urke and Stoller in 1992 and 1993, a PRL paper and a PRA paper. Okay, so okay, so here what happened that this is the blue one is a hybrid beam splitter. I will explain what hybrid beam splitter is, and this one is a simple beam splitter, right? So what goes that this is a particle with polarization H, and this path is R, and this goes in this way. This is another particle with polarization H and path L. This goes this way. This is for you can say phase shifter. This particle can go this way or this way. This particle can go this way or that way. And here is a PBS. Here you can after that this is a Mach Zehnder type of interferometer, and you can say there is a PBS. You can detect either H and V, and you can detect its part U and R. And hybrid beam splitter. Okay, hybrid beam splitter circuit. I think I have here. So this is a hybrid beam splitter. So hybrid beam splitter is consist of PBS1 and PBS2 and quarter wave plate. So this is just the mirror one. So this is the circuit of the hybrid beam splitter. Just put there. Okay. So here what we have done. So the initial state was BHBL, and after HBS1, so this state becomes BHR and IBP. So they are entangled in their internal degrees of freedom. And after this circuit is completed, this is the final state. You can just easily calculate by this circuit. And if you just analysis this circuit, you can have entanglement between the path and polarization degrees of freedom of these two particles. So this entanglement is then swapped between this H, the one particle of these degrees of freedom, another particle of path degrees of freedom. So we have proposed a circuit for entanglement swapping using two indistinguishable particles without using the Bell state measurement.
Can you give an example of 2 degrees of freedom that are different? Would that be like polarization and momentum?
Yeah, polarization or OM, orbital angular momentum, or polarization of path degrees of freedom, anything like that. Here we have used the external degrees of freedom, say path degrees of freedom. There are very new work are being, you can get that higher dimensional degrees of freedom, path and polarization, path and orbital angular momentum, and there are sometimes the 3 degrees of freedom are being entangled. There is also one paper that they have entangled 3 degrees of freedom of a single particle. So, in conclusion, we have overall proved that no hyperorbit entangled state for distinguishable and no unit fidelity quantum teleportation for indistinguishable. We have defined the D-wave traceout rule for indistinguishable. We have shown the maximum violation of monogamy for two. This is indistinguishable. Sorry, pardon me. For two indistinguishable particles, and this is just our ongoing work. Just so please ignore this one. And we have shown that two particle entangled swapping for two indistinguishable particles. Okay, so this is and in the future direction we can explore some more quantum properties and applications that are unique to either distinguishable particle and indistinguishable particle, and it is possible that that maximum violation of monogamy can be achieved for other quantum correlations such as steering, discord, coherence, etc. And we have to find some application of this maximum violation of monogamy of entanglement and also this entanglement swapping in the future direction. And this concludes my talk. Thank you.
Okay, great. Thank you.
Can these operations and discussion of all these techniques can make distinguishable to indistinguishable and vice versa?
Particles.
Yes.
Right.
Yeah, I believe you said that you would show how fermions can be indistinguishable.
Oh, yeah. Sure. So okay, I think I have that slide is not here. Okay, so we can just have this circuit and you can understand that. Okay, so here you can say that whatever you have told cannot have a two particle with same degrees of freedom, right? In this special location, but ideally we don't do this operation. Ideally, we do this particle swapping method, right? So what particle swapping method does? This particle swapping method just you can say destroys the identity, and these two particles belongs to two different spaces. So you can say here for fermions, this is now possible that two fermions become indistinguishable, and they can have, you can say, with that Pauli exclusion principle, this applies to here, right? You can say they are not in the same spatial location, but they are indistinguishable. So that's why I told you to wait at the end of the talk, but exactly you can know that how using fermions you can generate indistinguishable particles. If you just follow the mathematics, you will easily know that, okay, this Pauli exclusion principle, whatever you are referring, does not apply to this circuit.
But can this be done physically or only computationally?
No, this can be done physically. This can be done physically. We actually trying to, this you can say that this circuit only requires some linear optics, not a non-linear optics. And we are trying to experimentally do in one of our lab to perform this, and if we can successfully perform it, that paper will be available. But the challenging we are facing that to just to have this two degrees of freedom control of thing align operation. These are the experimental, you can say, difficulties that we are currently facing. Okay, the experimental is facing, but these are very much possible. You can just prepare it in your own lab.
You mentioned several applications: coherence, quantum steering. What is? Could you flesh that out a little bit? Give us an idea of a physical system that would, or an engineering application someday in the future for steering or coherence?
Till now, we don't know what are the ready application of steering, or Bell non-locality is the strongest one, but all we have the application of entanglement. And you can say for pure state, okay, just one thing I am clear, that most of the engineering application, they are done by the pure correlation overlap. Means there is only one correlation, that is entanglement. In the mixed state domain, this coherence, they become differentiated. Okay, so once we have some application that is applicable to only mixed state, then these pictures will come into play, right? Till now, whatever application you are getting in the engineering domain or any of the quantum domain, that is only using the pure state. So there are only a few applications that is possible with mixed state, like what the application I forgot, that is for mixed state. There are some application that is unique for mixed state, but currently there is no engineering application that you can do using mixed state. But in previous, if you design an experiment or application using only mixed state, then you can distinguish all these correlations, right? Just interesting to note, for pure state, they are a single one. That's why you till now did not get any specific applications like coherence, discord, stability, or Bell non-locality, because our most of the application are for pure state.
Well, why do they call it steering?
This is just a name, because the steering is, you can say that alternative of the, by definition it comes like steering. But because the steering is, you can say, two particles are far apart and you are doing some operation on one particle, and the state of the other particle is changed. So you can say this is just steered. You can changing the state of the particle in the other position. That is, it's called steering. Practically speaking, I am not an expert in steering or discord or coherence. I only know some entanglement and this Bell non-locality one. But this is very emerging topic, this steering, discord, and coherence, because this entanglement and non-locality are means kind of exhausted, and nothing much application is there. So if one just explore this steering, discord, coherence, there will be pretty applications.
All right. Do we have more questions? I can see that there were some questions on our chat, but let's maybe allow participants to unmute themselves and ask the questions if there are still some unanswered.
At some point you mentioned unitary transformation. So is there some
Itamar,
yes,
I think, yes, I think there are issues with your microphone, or at least it's difficult to hear what you would like to say. So maybe let's try once again.
Okay.
Or maybe you can just write your question on the chat. Maybe it will be easier.
Okay, I will do that. But do you hear me better or not?
Partially. So sometimes it's
Okay,
easier to understand, at least for me. Of
Yeah,
course, it's
okay.
important if our
So
if Dr. Das can hear you and understand the question.
Sure, Paul, I'm trying to hear, but I think it will be better if just he can write, or
yes,
you can ping me up, because
yes,
we cannot hear you. So my
Yeah.
email ID is this one. Please,
Mm-hmm.
I'm letting this on the chat.
Yes. So Itamar just posted a question, suitable unitary, but I'm not sure if this is sufficient.
Well, what I meant is
Okay, suitable unitary. So if your question is suitable unitary, so unitary is based on this value of k. Okay, so Bell state measurement. So we know that okay, so in the Bell state measurement, the output will be four type of outputs are possible. Okay, so based on
I'm not hearing
this
any of
output,
this.
you can apply unitaries. So
Itamar, please just yes.
I am telling the suitable unitary. This output y will be this output. They will apply different type of unitaries, and that will be predefined.
Okay.
Yeah.
Thanks, Dr. Das.
Yeah. So if there is, so I will share the PPT, so you can share the PPT to all the participants, and please share my email ID so that if anyone has, and also the LinkedIn profile, so if anyone has some more question, he can directly ask me. Okay, so that will be more convenient. And I know that people may have very good question because this distinguishability, indistinguishability, fermion, boson, these are very complicated topics. At last, for me, I still have some confusion, and I also need some person to ask my confusions.
Okay, good.
Yeah. Okay.
All right. Any more questions now?
I was wondering if I could ask a more mainstream
Yes.
question of
Please go on.
the presenter. You know, this room is full of learned theoretical and applied physical people. But is it possible for you to state in simple or somewhat more simple terms the concept of entanglement and this business of reading one of the bits and knowing what the other bit is there actually I've heard discussion where they say reading one bit actually changes the state of the other bit. Is that really what's happening?
Right. So if two particles are entangled, so if you perform some operation on one particle, then the state of the other particle may be changed. You can change the state of the other particle. That's what the concept of steering is. Right. So if you also can perform some operation, you can also say you can have A and B are entangled, not necessarily maximal, and A can entangle another particle, say C with A, then the state of the B will be changed because the entanglement will be distributed among A, B, and C. Right. So by
Okay, thank
this
you.
way, you can change the entanglement of B.
Okay. Do we have more questions now?
Yes.
Yeah, please go ahead.
Yes, please go on.
Okay. Hello?
Yeah. Please be louder.
The question is entanglement is limited only to a pair of particles, not to three, just because if a third one will be there will be a chaos. Because each other they can, by interaction, via entanglement, they can mix up each other. So the question again, am I right in my intuition that entanglement is only between two particles?
No. Entanglement can be between many particles. See, how I can say between two particles they can share say 100 rupees. Okay, so the 100 rupees is the maximum amount of entanglement A can share. So A can share this 100 rupees with only B. If A can share 100 rupees only B, then A get 50, B get 50. So A can share 100 rupees only A, B, and C. Then each of one get can 33, or there are infinite possibilities. Okay, A can share this entanglement with n number of parties. Then each of them can get some amount, right? But the total 100 rupees is fixed, or $100 is fixed. Okay, so entanglement is fixed, is between how much entanglement A can share, but it is not fixed that how they get sharing, but the amount is fixed. If two particles are maximally entangled, then they cannot be more entanglement with C, right? So this is the thing.
So this may be more a question of philosophy than physics, but a famous
Right.
scientist told me that everything in the universe is entangled. Is that to some degree? Is that your opinion?
Right. That is. See, as an engineer, what we want to do, we want to use something, right? A universe may be entanglement. So why you can say that why this entanglement and information thing is so much popular, and why did Alan Aspect and Anton Zeilinger got Nobel Prize today? They have done experiment 40 years back, but they got physics Nobel Prize today because today we have pretty much application of entanglement in QKD, quantum internet, quantum computing, etc. So in philosophy, you can say that whole the universe is entanglement and etc. etc. But what is the use of that? If you get something useful, then that is of some business. Then you might be interested. So here, what we are trying to do is the use of it. It's a practical use of it, right? In the phone, in the laptop, or in the QKD, in the secure communication, in the fast state quantum chemistry. If you are getting some application, then that is the use of it. If the whole universe is entanglement, that may be true, may not be true, but is that usable? If that is usable, then I'm interested.
Well, what I would say is, for those of us who are familiar with Bohmian mechanics, David Bohm's mechanics, that implies entanglement probably of everything. Would you agree?
Right. So this is their formalism in Bohmian mechanics. This is their formalism. But what is the use of it? If you get something usable from it, then I will certainly agree, and that I will certainly be interested to get more application of it. Right?
Thank you.
Yeah. Okay.
All right, great, thank you. Do we have more questions?
I think one question.
Right. Yes, go on. Please go on. Go ahead.
I have a question. has entanglement of particles been observed as natural phenomena outside of a laboratory or outside of what we currently refer to as qubits?
Right. Yes, it is currently natural phenomenon and quantum internet. There is a Chinese scientist. They did some space communication entanglement. Right. So this is just outside laboratory, and people are doing the free space communication from one building to another building. So this is not a laboratory phenomenon that only the scientists can do. This is just coming as common people's phenomena. And very soon, you can say in 3 or 4 years, we will have quantum internet and quantum communication. And just I can show you that there is also coming up new models of the phone that will communicate in quantum communication in quantum internet, and they will be using some photons through some channels like what we communicate.
So there is some natural phenomena that creates entangled particles?
Or natural phenomena. Okay, you were telling about some natural phenomena. No, that we don't know till now whether there is some natural phenomenon or not.
Inside a neutron star, I think you might get some entanglement.
No, natural phenomena is the decay of spin zero particle for two electrons, or electron and neutrino. It depends. So must have the same. Two particles must have the same momentum than the one from one decay.
Two particles that are created together in an experiment are entangled.
From decay, yes. You have decay from one particle to two.
Yes.
Yes.
This is natural case of entanglement particles. If you have spin zero, these two particles you have on the end must have the sum of their spin also be zero.
Right.
And they are entanglement.
Right. So we have some crystal BB barium borate 2. There are some crystal where we can send the photon and they count as a 2 photon where these 2 photons are entangled. This is the what I forgot the name. Non-linear generation of entanglement using some crystals, right? So you can say this is a natural phenomenon of entanglement generation, and we don't know that how this entangled photon are generated from this crystal. That is an active area of survey research.
And even with three particles, like in a particle accelerator, there are three particle reactions where there are collisions which generate a whole stream of dozens of particles, and they're all entangled. They're all entangled with one another.
Right. There is also another way of generating entangled, and we don't know that how they are getting entangled. That is a complete mystery that how they are getting entangled. But in this figure, what you can see that this particle exchange method, this is a quite simpler to use. Okay, there is no, you can say, mystery of getting people particles entangled. This is the most simplest thing that you can do mathematics, you can have a lab, and every time you can play with this setup. So this is the easiest way of generating entangled particles that I can see. And these two particles are never interacted. The interesting thing is these two particles never interacted, but still they got entangled. Okay.
All right. Any more questions?
I want one question.
Go on.
Please you share the slide and the record video is one, but I want the review to after, before and after.
Sorry, I did not get the question.
Review our learnings. Yes. Upgrade.
Pavel, did you get the question?
I'm not sure. Maybe you can repeat your question, please.
Please you share the slide and record video for me.
Yes, the video is recorded. The video is recorded.
Okay. And slide you share?
Yes, it will be shared later. Yes.
Not share. What?
The video will be shared. It's already recorded and will be shared in the YouTube. And the live stream is also available.
Helen has just posted a link to the live stream on YouTube.
Yeah.
Thank you. Okay, thank you.
All right. Okay. Any more questions?
Shared, it's already. Yeah.
Yes, I think that Itamar wanted to say something. Still issues with the microphone, I'm afraid.
I will connect by it's probably not this question.
Itamar, I think we cannot hear you now, so it's difficult to understand.
Okay.
So maybe you can try to write your question again on our chat, or maybe send an email later to Dr. Das.
Yeah, that will be very great.
Okay. Do we have more questions now? If not, then I think we can finish the meeting for today.
Yeah.
Okay, thanks, Itamar. Yes, you can send an email. Thank you. So Helen, I think we can stop recording. And with this, we would like to thank everyone for attending. And first of all, thank you, Dr. Das, for the great presentation and also answering all the questions. It was quite an interesting discussion. So I believe that our participants enjoyed and benefit a lot. So thank you.
Yeah,
and,
thank you.
Yeah, we are looking forward to meet all of you next week. On Saturday, there will be next meeting as announced. So we hope to see you then, and have a good day, have a good week. Thank you.
Thank you.
Yeah, bye everyone.
The